Hey guys, welcome to another session on maths for data sciences. So till now we have been looking at some of the more important distributions. In the last session we looked at normal distribution and some of their friendly properties of a normal distribution, and therefore in this particular session we'll be looking at one of the major application of normal distribution, which is called central limit theorem. Now, central limit theorem is defined for distribution of sample means of various samples drawn from a Bayes distribution or from any distribution. Now, the sample means, so for example, let us take an example of this particular distribution. So what we are taking, this is an example distribution that we have here. So there are four possible values of x, 1, 2, 3 and 4, and the probabilities for each is given here such that the sum of all probabilities is 1, and therefore this is a valid probability distribution for the random variable x. Now if we have to represent this distribution in a graphical form, let us say we are doing it using a histogram, and we have seen before that for histogram the bars have to be joined with each other. So let us say we get the limits for the bars as from 0.5 to 1.5, so that will have px equal to 1, which is 0.2. So let us say this is the bar and this is 0.2. Then for px equal to 2, which will lie between 1.5 and 2.5, the probability value is 0.3. So let us say this is the bar and this is equal to 0.3. Then for px equal to 3, which lies between 2.5 and 3.5, the value is 0.4, and therefore this is the probability. And finally for px equal to 4, it is equal to 0.1, and therefore this is the kind of histogram we have in this particular case. Now clearly this particular distribution, which is the Bayes distribution here, is non-symmetric and non-normal. So clearly the distribution given here is nowhere close to a normal distribution. We can see that it has a longer left tail here, so this is more like a left tail distribution. If you remember the skewness, this is a left skewed distribution or a negative skewed distribution. So central limit theorem, the beauty of central limit theorem is, irrespective of how your Bayes distribution is, if we take a lot of samples from this distribution and then we plot the means of those samples, then the distribution of means of those samples would always be a normal distribution. So let us say we take some samples here. So let us say we take a total of 1000 samples. So the first sample, let us say we are taking a sample with a certain sample size. So let us say we are taking a sample size of 5 here, and the first sample we got is 2, 2, 3, 3 and 4. Let us say this is the sample. Now the sample mean computed from this particular sample would be what? 2 plus 2, 4, 7, 10, 14 upon 5, which is 2.8. So we are just calculating the sample mean here as sum of the ratio of sum of all values with the total number of values, which is 5. So n equal to 5. So this is the sample size here for each of the sample we are going to take, and we are going to take a lot of samples here. So then we get S2. So let us say this comes out to be 1, 2, 3, 3 and 4. And now the sample mean for this is, the sum is 2, 3, 6, 9, 13 upon 5, which is 2.6, and so on. So once we have done that, we get a lot of samples here. So let us say we take 1000 samples, and for the 1000 sample also we get the sample mean. Let us assume it is 2.4. Now once we have got these 1000 samples, what we need to do, we plot these sample means. So these are the sample mean values here. So 2.8, 2.6, 2.4, and similarly we would have a total of 1000 of these sample mean values. So once we have done that, what we would notice is the values which we are getting would look something like this. That is like a normal distribution, which was not the case with the Bayes distribution. So irrespective of the shape of your Bayes distribution, we would always get a distribution of sample means as roughly normal. So it need not be exactly normal, but the distribution of sample means have to be roughly normal. So this is the central limit theorem. So I'll just repeat it once again because this is one of the most important theorem in statistics. And the theorem states, irrespective of the shape of your Bayes distribution, it could be non-symmetric, non-normal, skewed, or high kurtosis and things like that. The distribution of sample means, given a certain conditions, which we'll see later, the three conditions, given that those three conditions are satisfied, the distribution of sample mean would always be a normal distribution or an approximately normal distribution. It need not be exactly normal, but it will be approximately a normal distribution. Now, the conditions for central limit theorem to hold are, so they are pretty intuitive assumptions. So the sample size n has to be sufficiently large. So the thumb rule for central limit theorem is that n should be greater or equal to 30 in general for the central limit theorem to hold. Then the samples drawn are independent and identically distributed. Now, since we are getting all the samples from the same Bayes distribution, which is this particular distribution, therefore they would always have an identical distribution. Also, the selection of one sample should be independent of selection of the other sample. So it's not like the probability for selecting a particular number changes in a particular sample given that that number has been selected or not selected in another sample. So all the samples should be independently taken out from the Bayes distribution or from the population distribution, you can say. Yeah. Finally, the population, which is the Bayes distribution, should have finite mean and variance. So by this we mean, let us say we try to calculate the mean and variance of this Bayes distribution here. Now the Bayes distribution mean is computed using the expected value, which is mu equal to Ex, and we have computed these kind of terms before. It is the sum product of x with the corresponding probabilities. So it's 1 into 0.2. So 1 into 0.2 plus 2 into 0.3 plus 3 into 0.4 plus 4 into 0.1. This becomes 0.2 plus 0.6 plus 1.2 plus 0.4, and this comes out to be 2.4. Yeah, so this is the mean of the population, and clearly it's a finite value. Now to compute the variance, again we have seen this before. It is computed as the difference between the second movement of x with the mean square, and one can compute now this as, so second movement of x is computed as 1 square into 0.2 plus 2 square into 0.3 plus 3 square into 0.4 plus 4 square into 0.1 minus 2.4 square, because the mean value is equal to 2.4. This becomes 0.2 plus 4 into 0.3 is 1.2 plus 9 into 0.4 is 3.6 plus 16 into 0.1 is 1.6 minus 2.4 square. Now this is 3.6 plus 1.2 plus 0.2, which is 5, plus 1.6 minus 2.4 square, which comes out to 0.84. So this is the variance of the population here. So we can write it as sigma square, and the mean was equal to 2.4. So these are the population parameters here, which are the mean and the variance of the population, and we represent the parameters for the population as mu for mean and sigma square for variance. So this is defined for a population. But now let us say we have got a lot of samples, and let us assume the sample size was n, and for the sake of using the central limit theorem, let us say the sample size which was drawn was 50 in our case. So now we have to compute the mean and variance of the distribution of this sample means, which is a normal distribution. So let us say we have the population mean as 2.4 and population variance as 0.84, and the sample size to calculate the mean in each case is 50. So how do we compute the distribution of the sample mean itself? Now how we do that? First let us define the sample mean. So it is computed as x bar. So we denote the sample mean as x with a bar on top of it, and it is obviously computed as the sum of 50 values in this case for x, which are randomly selected, divided by the sample size, which is n equal to 50 in this case. Now let us say we have to compute the mean of this particular expression. So how we do that? So the mean of the sample means distribution is computed as expected value of xi upon n. Now for an expected value operator, we have seen that we can bring the constant out as it is, and therefore we are left with expected value of summation of xi, which is nothing but sum of all the values, all the n values here. Now expected value of any x value is nothing but the mean, because any x value is randomly selected from a particular distribution, and the expected value gives the expected value of any sample value taken from a distribution is nothing but the expected value of the population, which is equal to the mean of the population. So for any sample drawn xi, the expected value is equal to mu. So this can be written as 1 upon n expected value of x1 mu, x2 mu, and so on till n terms are there. So there are a total of n terms here, and therefore this can be written as n mu upon n, which is equal to mu. So the distribution of sample means, which we have got here in the previous slide, so just like we saw here, so these were the various sample means which were collected, and we had got a approximately normal distribution for the sample means according to the central limit theorem, and the distribution of this sample means is normal with a mu as same as the population mean. But now let us try to calculate the variance of this sample mean distribution as well. Now to calculate the variance, so let us calculate it here. So variance of sample mean is computed as variance of summation xi upon n. Now for a variance operator, the constant can be brought out of the variance operator only after squaring it. So I think this we have not seen before, so I'll just mention it here. The constant can be taken out from a variance operator only after squaring it. And therefore we are left with variance of sample mean as variance of summation of xi divided by n square, because we have to square the sample size here. Now we are adding the variances of each sample point here. Now if you remember, we had assumed that each sample point is independently selected. If you remember, this was one of the 3 assumptions to apply the central limit theorem. Now since each sample point is independently selected here, we can add the variances. So variances could be added only if variables are independent of each other. which means variance of A plus B is equal to variance of A plus variance of B only if A and B are independent variables, which is the case here. Now once again, since we are adding the variance for each xi around 50 times, so we are left with variance of sample mean as n times the variance of xi divided by n square. Now the variance of xi is sigma square, which is the variance of the population, divided by n square, and therefore we are left with sigma square upon n. So the variance of sample mean is actually not equal to the variance of the population. It is computed as the ratio of the variance of the population and the sample size n. Now another important metric which we would be using a lot is called a standard error of sample mean. This is nothing but this is the standard deviation of distribution of sample means obtained from an underlying distribution. Therefore, to find the standard deviation, since we know the variance of sample mean, we just do the square root and we are left with, so standard error could be written as SE, which is nothing but standard deviation of sample mean, which is computed as sigma upon root n. So we just did the square root in both the sides to get the standard error of sample mean. So this is also called the standard error of mean or standard error of sample means, and it is computed as the standard deviation of the sample mean distribution or the distribution of sample means obtained from an or underlying distribution, just like we saw for this particular distribution. Therefore, the sample mean, this is the distribution we obtained from the sample means using the central limit theorem. So this theorem would be used in a lot of instances in various projects in finance and in data science in general, because it is easier to study normal distributions as compared to the non-symmetric or skewed distributions, and therefore we normally take a lot of samples from an underlying distribution and instead study the distribution of the sample means, which is a normal distribution, provided that the sample size is large enough, which is normally taken to be greater than or equal to 30 as stated here. So yeah, so this is how we also compute the sample means of the sample mean, which is same as the population mean, and also the standard deviation of the sample means, which is computed as sigma upon root n, and it is also called the standard error of mean.